Okay, Euler's method, section 2.6. This is basically treating you, the human, like you're a computer. Okay. Sometimes it's physically impossible to solve a differential equation explicitly, right? In that case, if we can't get a closed form expression of y as a solution, we need to numerically approximate solutions at some point x naught, right? And usually this is good enough, right? For most practical applications, getting an approximation of the solution near some initial point is okay, right? It's not always the best case, especially if you need to evaluate, like if we're given this initial condition, so we know that at x naught the function goes through this point y naught, and you want to know the solution far away from that, that can be a bad time to approximate. But if they tell you the function value at, like, say, x equals 1, and you want to approximate at x equals 2, well, that's not too far. That's not too bad. And normally, I mean, there's other methods to do this. There's like the RK4 method, and there's higher order methods to do this approximation, but the most basic approximation is Euler's method. It's very algorithmic, it's very boring, it's very calculator intensive, but it gets the job done. And it's very easy to code a computer to do this for you. Right, so humans, right, a human can do Euler's method, you can do like 20 steps, maybe 20 steps. If you're very careful and you're very focused, you can maybe get a 20-step approximation. But the computer can do a 10 million step approximation, right? The computer doesn't get tired and it doesn't mess up inputting things into a calculator. Anyway, the point is that usually if you ask a computer to calculate some value of y, right? If you want to know y at x1, say, given y at x naught, the computer can do this for you very quickly. And that's the usefulness of this. Okay, let's talk about Euler's method to numerically approximate solutions of a differential equation. Let's say we did have an explicit solution to this differential equation, right? Then close by, right, near, this is like big air quotes here, big air quotes, nearby to this initial point, right? The tangent line to the solution curve is going to be close to the solution curve. Okay, let's look at a picture. What am I trying to say? Let's say we have this setup, right? We have this setup. This is our actual solution. We can find this via, I don't know, exact equation, separable equation, linear equation, substitution. There's some method we can employ to get an actual solution. And this green line is the actual solution to the differential equation. Now, in the statement of the problem, right, they give us an initial condition, right, which means this point here, right, corresponding to some y0, this point here is given. This is given to us, right? This is a fixed point. This is a fixed point. And we know it, right? Now the question is, can we approximate the value of y at some point x1? Right? Can we approximate this red dot up here, which is the value of the actual solution at some other point x1? Right? So this y1 is the actual value of y at x1. right? If you start at x1, you go up to the function y, and you go across. This is the true value, yx1. However, near this point, right, as long as you're like close, the tangent line to the solution curve is fairly tight, right? It's fairly close to the actual solution curve, right? So as long as you take a really small step going from x0 to x1, the tangent line, the linearization of y is close to the true value of y, right? The linearization of y is close to the true value of y. So, the idea behind Euler's method, is you start at the point x0. We do not know the green curve. But we were given a differential equation that starts out dy dx equals some function of x and y, which means we can calculate the slope of the true solution using the differential equation they handed us, right? What is y prime? That's the slope of the solution at some point xy. Right? So here's how Euler's method goes. You want to travel a long way. And you want to approximate the solution here. Now, in order to do that, you need to take lots and lots of small steps. So what you do instead is you start at x0 and you walk along the tangent line to some approximation of x1. Then you draw a new tangent line and you walk along it to get to some new approximation of x2. And then you draw another tangent line and approximate x3. And then you draw another tangent line and approximate x4. And before you know it, you've approximated xn. So we're going to chain together lots of these linearizations, right? We're going to linearize a bunch of times, and we're going to get some error, right? But you'll be able to obtain an estimate of the solution at some point xn by chaining together lots and lots of little steps. I hope that made sense as far as processes go. The algorithm is actually really straightforward, but as terms of like intuition, right? This is what the computer is doing. It does not know the green curve, but you gave it dy dx equals some function of x and y. So we can find the slope of this tangent line, and we know the point that this tangent line passes through. So we can calculate a linearization of that. And then we can find this new point. And then we can take another step. And then we can take another step, and another step, and another step, and another step, and eventually we'll get to xn. Okay. Let's do an example. Oh, not yet. Obviously, yeah, this process works best if h is really tiny, right? And in this case, when h is small, remember that I didn't say it here, but h is like my step size. H is like the step size, right? H is like the step size. So to go from x0 to x1, you just take x0 and add a little bit, right? So when the step size is small, the error is also small. And in this case, the actual y1 should be approximately equal to, right? Approximately equal to the original y0 plus you move along the slope h units, right? You move along the slope h units. And here h again is called the step size. So if the value that you want to estimate is far away, you can just take lots of little steps to get there. This is what's called Euler's method, right? Given an initial value problem, y prime, or sometimes it's written as dy dx equals f, right? And some initial condition. You can estimate y at x final using like in many steps in this way. Here's how you do it. To get the step size, you take the final x and you subtract the initial x and you divide by how many steps you want to take to get there, right? So for example, if I want to go from x naught equals 1 all the way to x final equals 5 using n equals 600 steps, right? Then h would be 5 minus 1 over 600, which is 4 over 600, which is 2 over 300, which is 1 over 150, right? So in the case where I'm going from 1 to 5 and 600 steps, my step size is 1/150th. Does that make sense on how to get h? I hope so. So if I'm going from 1 to 5 and 600 steps, to my step size is 1 over 150. Okay, given that step size, we can now calculate x1, x2, ... all the way up to xn. And this xn will be equal to x final. Oops. X final. Okay. And now, to get an estimate of y1, right? To get an estimate of y1, I'm going to do y naught plus f at x naught, y naught times h. And then to get the second y, right? This is associated to x2. To get the y associated to x2, I just start at y1, right? Start at y1, and then I walk along the tangent line at x1, right? To get y3, I start at y2 and I walk along the tangent line at x2 until we get to y final, which is the nth step, which is the previous y plus the previous f of the previous x, the previous y, and h. Now, if you have the actual value of the solution at the nth point, then you can calculate what's called the absolute error and the percent relative error, right? The absolute error is the absolute value of the actual value at xn minus your approximation, right? Minus your approximation. And to get the percent relative error, you just take the absolute error over the actual value times 100, and that gives you what's called the percent relative error. How about an example? Now this is going to be the only example we do because it's very tedious to do these out, but I think your homework makes it easier on you. So consider this initial value problem. Y prime equals 0.2 xy, y of 1 equals 1. So this is my x naught, and this is my y naught. And I want to approximate x final of 1.5 using h equals 0.1. So I'm going to start at 1, and I'm going to take steps of size 0.1 until I get to 1.5. And then, after you do this approximation, right, I'm going to solve this initial value problem and calculate this error at each step. And I'm going to round everything to 4 decimal places. So this, right, this is dy dx equals 0.2 xy, which is separable. Oops. So this thing here is separable, right? I can separate these and solve it. I can solve this exactly, but I'm going to use Euler's method first. Here we go. Here's the table that I always set up, right? Here's the table that I always set up. The first column is the x's I'm going to step to. The next column is my approximated value, right? This is my approximation. My approximation using Euler's method, right? That's this guy. So these first two columns are Euler's method, right? This is Euler's method. Okay, after I've calculated those two columns, I can solve, right? It's a separable equation. So I can solve it exactly and find the real values of y at all these points x. Right? Because it's separable, I can find all of the true values of y. And then I can use those equations to calculate the absolute and relative error of the approximation. Right? This uses the approximation and the actual value of y, right? That's the setup. So every time I do one of these Euler problems, I get this table, right? I get my x's, my y's, my actual, my absolute error, my relative error. Now, I know that I'm starting at x naught equals 1.0, right? I'm starting at x naught equals 1.0. So this is my x naught. This is x0. This is x1. This is x2, x3, x4, and x5, right? These are my x's. I also know y0 because it was given to me. It was given to me. I know that y0 is exactly 1. That's going to be my first step of approximation, and it also happens to be the actual value of y at that point, because this is the true solution, right? Not approximated. Not approximated, the true solution. So we're going to just fill in this table, right? First, I'm going to actually calculate the actual answer because that is straightforward, right? So this is a separable equation, like I said before. All I need to do is move the y's to one side and the x's to one side, right? So 1 over y dy equals 0.2x dx, which implies this is my y, and since y of 1 equals 1, I know c equals negative 0.1, so y of x equals this equation. This is my explicit solution. Need this to calculate the error, right? This is my actual solution, right? My actual solution in a closed form. So I can find the value of y, right, at all the different x's. So I can use this explicit solution to fill in this column. Right? I can just plug in x equals 1.1 and find the actual value using this explicit solution. Okay, that was easy. That was easy. Now let's fill in this column, right? This is using, again, Euler's method. Euler's method will fill in this whole column, right? How do we do it? How do we do it? You initialize the algorithm. X naught equals 1. Y naught equals 1. My step size is 0.1. My function f is 0.2xy, right? This is f. This is f of x and y. Right? This is f of x and y. We need to find y5, right? Since it'll take us 5 steps to go from 1 to 1.5 using the step size. So what do? Well, the first thing we do is we calculate y1. Whoops. We calculate y1, right? And y1 should be, this is the same every single time, right? y1 should be y0 plus f of x0, y0 times h. Every single time. And since I know f, I know x naught, y naught, and I know h, I can just plug in the values. Right? I can just plug in those values. Y naught is 1. F of x naught, y naught is 0.2 x times y. Right? So 0.21 times 1. And my step size h is 0.1. Which means my approximated value of y1 is 1.02. 1.02. Okay, that's one step of Euler's method. Then I start again. y2. To get y2, I need to take y1, add 0.2 x1 y1 times h. And I know right here, this is y1. Right? And I know x1 is going to be 1.1. Right? Since I'm taking 0.01 steps, x1 is 1.10. Right? So again, y1 is 1.02, 0.2 x1 y1 times h again, 0.1. This gives me my second point estimate, y2, 1.0424. Okay, this is when it gets a little annoying because now you're carrying around more decimal places, but it's the same process every single time, right? So again, to get y3, you take the previous y, you add to it f of the previous y and x times h, every single time. To get the next y, you take the previous y plus f, add the previous x and y times h. So, y3, here's y2 plus 0.2 x2 y2 h, which is this. And then again, y4. And again, y5. Now, this y5, this is my approximated value at x final, right? This is my approximation of y at x final. This is y at 1.5 approximated. This is my approximation of y at x equals 1.5. Now, I can calculate the actual value at 1.5, right? I can calculate the actual value at 1.5 using that closed form solution I had earlier, right? Where is it at? This guy. E to the 0.1 x squared minus 1 tells me that the actual value at x equals 1.5 is this, which is 1.1331. Therefore, my absolute error at the final step is actual minus approximated absolute value, right? Actual minus approximated absolute value, which is this number here, 0.0073. That's my absolute error. And my percent relative error is the absolute error divided by the actual value times 100. So that's a 0.64%, right? This is a percent. 0.64% error. Now, I can do the same game for the absolute value and the relative error, or absolute error and the relative error all the way down the table. And here's what we get, right? We get these values of x that were given to us. These are my approximated values that I did using Euler's method, right? These are Euler's method. These are the actual values, which you get from plugging into that e to the 0.1 x squared minus 1 equation, right? These are the actual values. And using these, I can calculate the absolute error. And then once I have the absolute errors, I just divide by the actuals and multiply by 100, and I get my percent relative errors. My percent relative errors. That's Euler's method. That's all it is. It's just a way to approximate solutions. And it's very algorithmic, right? This is the algorithm every time, right? It repeats itself. To get the next y, you take the previous y plus f at the previous x and y times your step size. That's it. That's it. Okay.